All right, class, happy Halloween. We are now on module 11. Today you have the exam opened up, right? Make sure you do your exam. I think there's a practice writing assignment due today as well. So any questions about anything before we start module 11 today? All right, so we're going to talk about polar coordinates, right? Which they often use at sea. Okay, so instead of X and Y, right? How far you go left and right and how far you go up and down. Another set of coordinates could be R and theta, right? So you could see if you were at C, you kind of might, if you're right here, you might want to know like which direction to look in and then how far to go in that direction, right? That might be more useful than how far to go left and right and up and down, right? If you're at C, all right? So you want to turn and then go in that direction, right? And C, you don't want to travel like this, right? You kind of want to know what angle do I need to go in and how far do I need to go. Does that make sense? So uh, then you can also go to 3 dimensions, X, Y, Z, and then you would have R, theta, C, right? So you'd have an angle like around you and then an angle like, up and down and then how far to go in that direction, right? So you'll see that some equations, like for a circle, right, you have x squared plus y squared equals, say, 9, right? Y'all know that's a circle of radius 3, right? Now, if you don't know the Pythagorean theorem or anything and you look at that, you might not just intuitively realize, oh, that's a circle, right? But this equation, even if you knew like no math at all, you might be able to look at that and go, everything that's a distance 3 from me, well, that's a circle, right? So here there's two variables to describe a circle. Here there's only one, right? So you can see there's different advantages and disadvantages to different coordinate systems, and there are a lot of coordinate systems, right? So we're going to learn the very first most basic one, right? Other than our X and our Y, also known as Cartesian coordinates, we're going to polar now. One thing we want to be able to do is switch between the two, right? And in this class, if you don't know where to start, you basically always start off with the Pythagorean theorem, right? So that automatically tells us R is the square root of x squared plus y squared. So if we know x and y, we can definitely get R, right? And what's the next three things we learned in this class as far as trig? The definitions, right, of sine, cosine, and tangent. Uh, Sine theta is y over r. Cosine theta is x over r. And tangent theta was y over x, right? These are the first four things we basically learn in here about trig. Right? Well, this one tells us that y is r sine theta. This one tells us that x is r cosine theta. So if we know r and theta, we can get y. If we know r and theta, we can get x, right? And this one tells us that theta tangent inverse of y over x. So if we know y and x, we can get theta. Here, you have to be careful though. Because remember, tangent inverse always gives you something on the right side of the circle, right? If you're talking about a coordinate that's over here, you might need to add pi to that sometimes, okay? That's the only subtlety here. So these equations allow you to go between x and y and r and theta. That's just the first four things we learned. So let's look at some examples here. So here's a polar grid, right? So here's a point, the angle here is pi over 4, and then the distance we travel is a distance of 2, right? So if you just see these two numbers, you kind of have to know what coordinate system you're in to know how to interpret them, right? Usually you see pi, you start thinking angles, right? But pi is just a number, isn't it? If you didn't know this was polar, you would be like, okay, 1, 2, and then go up pi over 4, right? These are not the same. This is not the same as this, all right? So you need to know that this is polar, because otherwise, if you read it like that, you're going to get a totally different point, right, in space. Does it make sense? All right, so you need to know, that's why your calculator, you have to tell your calculator, you have to change the mode to polar. So it knows to interpret the coordinates as r and theta and not x and y. Does this make sense? All right, so not the same. All right, you can see that because, what would this be? 8 pi over 4? No, 9 pi over 4 points in the same direction as pi over 4, doesn't it? Those are the same points. Okay, so 2 pi over 4 is the same as 2 9 pi over 4. But if you did it in Cartesian, up here, here's 9 pi over 4, right? These would be two totally different points. Whereas in polar, they're the same point in space, right? So there's one big difference between polar and Cartesian. Cartesian, for every x and y, that's a unique point, right? If you change x or change y, that's a totally different point. Over here, you can have all kinds of numbers for your angle. As long as it points in the same direction, that's still the same point, right? So there's a major difference between the two coordinate systems. Got a couple more here. Still our polar grid. All right, so we want 3 pi over 2. Okay, straight up, that's pi over 2, a distance of 3. Boom, there it is. 3 pi over 2. This is the same thing as what? 0, 3. Here's our r theta. This is our x, y. Okay, let's look at this one. 2 pi over. Notice how when you do this, you really look at the angle first. It makes you wonder why they didn't do theta r instead of r theta, right? Like if you're at sea, they're like, go 100 miles. In which direction? Oh, this direction, right? When you want to know the direction first and then how far to go, right? But it's written backwards, so that's how it is, all right? So pi over 3, let's see, that's like that way, and then a distance 2. Boom, there you go. And we could figure out what that point is in xy just using our knowledge of the unit circle. Let's see, on the unit circle, this point here would be, what, 1/2 root 3 over 2, right? But we want to be a distance 2 away, right? Not a distance 1. So this would be 1 root 3, right? Plus bar, you're just scaling out, right? So you can use your knowledge of the unit circle to figure out how to get further away, all right? Here's another example. Here they gave us a negative radius. Like, what the hell does that mean? In applied math, you never have a negative radius. It's, well, here's pi over 6. There's pi over 6. So the radius being negative just means go in the opposite direction. So we'd be over here, right? The obvious thing you didn't intuitively, a negative radius means go in the opposite direction. But I mean, in applied math, you'd never have a negative radius. The radius is always positive, right? Instead, you would write 2 and then what, 7 pi over 6. But they just want to make sure you understand the negative radiuses. So let's look at these. They want these on the same thing. So an angle of negative pi over 6, I'll do this one in red. There's negative pi over 6. We want to go distance 3. Okay. 2, 9 pi over 4. Let's see. 8 pi over 4 is all the way around. We'll do this one in green. Right? So here's 9 pi over 4. We want to go a distance 2. Notice that this is the same as the other point that we had, right? Because pi over 4 and 9 pi over 4 point in the same direction. It could have had the exhaust blowing in a different direction. So. All this grid computing stuff, all the computers, you know, the grid computing, like cloud computing, right? The energy required to run like all of the computers processing all that data produces more carbon than the entire airline industry. Right? That's a lot of processing. So we could figure out how to make like computers like more energy efficient. It would save a lot of damage to the environment. They're starting to find a way though, because there are physical limits as far as processing. We have entropy and heat being produced. We don't need the heat, right? Making developments in momentum computing. So here's our conversions. I've already. Here we go. So here's your standard triangle, right? You have x, y, theta, r, right? And from our definition, we have x is r cosine theta and y is r sine theta. Y'all will be using this for the rest of your lives, bouncing between these two coordinate systems. It's going to be natural for you, right? Anytime you see x, you're always going to think r cosine theta and vice versa. It's going to be wired into your brain from here on out. Good. An example. So here is a polar coordinate. What is it as rectangular? Well, let's see, where is this thing? It says pi over 2, that points straight up, and go a distance 3, right? I could tell you right now that this is 0, 3, just by eyeballing it, right? Does that make sense? Pi over 2, point straight up, go a distance 3. Well, that's the same thing as 0, 3. Let's see what our math says. It says x is r cosine theta. R is 3. Theta is pi over 2. Cosine of pi over 2 is 0. So this is 0. And y is r sine theta, which is 3 sine of pi over 2. Sine of pi over 2 is 1. So we get 3. So the math works out, right? All right, here's a polar coordinate. We have an angle of 0, but we want to go a distance negative 2. So we'd have to go in the opposite direction. That's where we're at. So in Cartesian or rectangular coordinates, this would be negative 2, 0. Huh. This is the point where they're the same, huh? That's interesting. Let's see what the math says. X is r cosine theta. R is negative 2. Cosine of 0 is 1. This gives us -2. And y is r sine theta. Sine of 0 is 0. All right, so there's one of the few points where they're the same in Cartesian and rectangular. All right, so let's see. 2 pi over 3 would be over here. So we want to go at distance -1. So that means we've got to go over here. Distance 1. Boom. Well, what would that be in rectangular? Well, we know our unit circle, right? We're distance 1 from the origin. We're on the unit circle. This would be, what, -pi over 3? So we know this, right? We don't have to use the math. We can use our knowledge of the unit circle, right? Let's see, the x value would be, what, √3 over 2? No, 1/2. And the y value would be -√3 over 2. Let's draw this a little better. Yeah, that's better. More accurate, right? But let's look at the math, right? So when y'all do these, try to do them in your head using, right, your knowledge of the unit circle. So you really get that unit circle down, and then do the math, right? X would be r cosine theta. R here is -1 with 2 pi over 3. Cosine of 2 pi over 3 is what, -1/2. So -1/2 is a half. That's what we got here. Y is r sine theta. The minus sine of 2 pi over 3 is √3 over 2. Is what we got here, right? So the math works out. So we get Pythagorean theorem, and then your 3 most important trig definitions. And you have everything you need to know. Right? First 4 things we learned. Everything we need to know for this entire section. All right, rectangular coordinates 3, 3. So rectangular to polar. 1, 2, 3, 1, 2, 3. Boom. Well, let's see. I know that this would be pi over 4, right? Because we've gone to the right 3 and up 3. What would my r be, though? I don't know. Going 3 that way and 3 that way, right? Well, r is the square root of x squared plus y squared, right? X is 3, y is 3. This is the square root of 18. 18 is 9 times 2. This is 3√2. There's r. So 3√2, and we already know the angle is pi over 4. We went to the right 3 and up 3. Does that make sense? We'd say, what is theta? Well, we know that tangent of theta is y over x, which would be 3 over 3, or 1. If tangent theta is 1, then theta has to be either pi over 4, or what about this? -3 over -3 is also equal to 1, right? So when we solve this equation, you have to know what quadrant your point is in order to solve this equation, right? This would be 5 pi over 4. But we know it's not that one. because our coordinate is in quadrant 1. Does that make sense? Yeah? All right. That's what all this is talking about. And it's also mentioning the fact that you could use 9 pi over 4. All right? Because those point in the same direction. This is a whole long explanation of those two simple facts. Here's where it gets fun. Equations. Not just a point, right? Can't do much with a single point. We like equations, right? Now you look at this. I already told y'all that this is the same thing as a circle of radius 3. This is the same thing as r equals 3, right? X squared plus y squared equals 3 squared. Okay, well, let's do our substitutions here, right? X is r cosine theta. Y is r sine theta. So this is the same thing as r squared cosine squared plus sine squared. And this is just 1, right? So it's the same thing as r squared equals 9. Or r equals, we could do positive negative 3. Well, that's two different equations, right? That's r equals 3, and this is r equals minus 3. Well, those are both a circle of radius 3, aren't they? We really only need one of these. So this is much nicer than that. So when you're talking about spherical stuff, we usually use spherical coordinates, or polar. Spherical is 3D polar, okay? Like if you're doing like astrophysics, it's like stars and planets. Pretty much everything in the universe is spherical, isn't it? Just the way it is because of gravity. It's because we have 4 forces, right? And forces fall off the further away you get, the weaker a force is, right? So forces have to do with the radius, right? They depend on the radius, how far away you are, right? How far away you are from an electron, right? Depends on, the electric field, right? So like gravity falls off as the distance squared, right? So the thing is you could pick your origin to be anywhere in space, right? Like I'm my own origin. I could have a spherical coordinate system around me, right? So if we're talking about 1 over r squared at when r is 0, meaning your origin, this thing craps out because you can't divide by 0, can you? Right? So if gravity falls off as 1 over r squared, that means at the center of every star or the center of any sphere, there's an infinite gravitational field, right? The gravity is infinite. No, that's not true, right? That's just a quirk of the coordinate system you chose to use, right? So if you switch to Cartesian, you wouldn't get infinity. You wouldn't be dividing by 0. So there's tons and tons and tons of different coordinate systems. They all have advantages and disadvantages, right? This is why even though general relativity predicted black holes, it took like 70 years before we actually thought they were real, right? We just thought it was a quirk of the coordinate system, right? So the biggest hassle of general relativity once it was discovered was trying to figure out the interpretation of it. Is this actual reality, a physical reality, or are these things quirks of coordinate systems? So you switch different coordinate systems. So you have like the Coulomb potential for like an electron, right? It's like what is the electric field at an electron? Electrons being the point particle. Well, the electric field falls off as 1 over r squared, so the equations would say the electric field is infinite, but it's clearly not. So one trick we do in physics is we say, we'll use our spherical coordinate systems, but instead of saying what happens exactly at r equals 0, we look at what happens when you're infinitely close to r equals 0. Which isn't the same thing. And then you get an actual number, right? I call it perturbation theory. And basically, you take your equation and you just slap it a little bit, make things vibrate. So like if you're looking at like the sky and the reflection of the sky in a lake that's perfectly calm, you can't even tell where the lake and the sky end and begin, can you? It's a perfect reflection, right? So you have to break the symmetry. So you slap the surface of the water, look at the ripples, and now you can see the total difference between, right, the lake and the sky, right? So that's what we do with our equations. It's called perturbation theory. And that helps us figure out if some of these artifacts are artifacts of the coordinate system or the physical reality. So that's some of the fun that y'all are going to eventually get to do. Y'all keep going with your mathematics. Breaking symmetries. Let's look at this one. So this one, it's kind of like the last one, but they stuck this y over here. So I look at that and I'm like, well, it's not a circle anymore. I don't know what the hell that is, right? I can't even solve for y to make it a function. So this, we can't write this as a function, not in terms of x and y, right? Right? We can't solve for y. We can't write it as y equals some stuff with x's in it. Can't do that. This looks circular. Um, what can we do here? If we switch it to polar, you might automatically recognize that's r squared, right? Now you could do what we did earlier and be like, okay, x squared is this, y squared is that, factor this out, and you get r squared. You can do all that, but you want to develop intuition so that you can look at that and go, well, that's r squared, and then y is r sine theta, right? And here we have r's on both sides. This would just be r equals 6 sine theta. So this is a whole lot simpler than that, right? One thing we can actually see that this is a function. This is f of theta. We could actually solve for r and write it into, there's not r's everywhere. Like up here, there's y's everywhere. You can't get y by itself. But in polar, you can actually write this as a function. So how would we graph this though? Right? I still don't know what does this look like, right? Well, let's see. If theta is 0, then r would be 6 times sine of 0. Sine of 0 is 0, so we get 0. So 0, 0 would be a point on our graph, right? Let's see, if theta is, say, pi over 6, then r would be 6 sine of pi over 6. Sine of pi over 6 is a half, right? This is 3. So at pi over 6, I got to go a distance of 3, and so on. So let's cut to the chase and look at the picture. Here's what it turns out to look like. So right here, at an angle of 0, you get r equals 0. At an angle of pi over 6, you get 3, right? At an angle of pi over 4, you're getting whatever that r is, right? At pi over 2, you get r equals 6, right? So it does look like a circle. I don't know if it is a circle. Looks kind of ovalish, right? 3 to 3, yeah, that's a circle. Because across here is 3, or is 6 and 6. So this is a circle. It's just shifted. It's shifted up by 3 notches, really, is what that is. Which we could actually rearrange that. What would a circle, that would be x squared plus y minus 3 squared equals, and it's a circle of radius 3, so we could turn this into that. This would be a circle shifted up by 3, right? So these, you'd have to turn this into that in order to realize that's a shifted circle, okay? Or you can look at this and go, that's a shifted circle, right? Okay. So here's something in Cartesian. We want to go to polar. what does this look like? Y'all know this is a line, right? Here's our y-intercept, has a slope of 3, looks like that, right? So it's intuitive in Cartesian, right? Straight lines are not intuitive in polar, right? Polar coordinates, everything's circular, right? If you hold theta, or if you hold r constant and change theta, you get a circle. However, if you hold theta constant and change r, you do get a straight line, right? But in polar, any straight line has to come from the origin, like that. A shifted one like this, let's see what it does. Let's change y here with r sine theta. We'll change x with r cosine theta. There you go. That's not intuitive. Maybe if we got r right by itself, right? If we made it, like here we have y equals stuff with x's in it. Can we change this to r equals stuff with thetas in it? We could do that. Let's see if that helps with intuition. And let's see if I factor out the r. So I divide both sides. At least I wrote it as r as a function of theta. I wouldn't look at that and go, that's a straight line, right? Obviously this helps, right? This is way better, right? Y-intercept, slope. I wouldn't know how to look at that and go, oh, obviously that's a line that goes through this point, right? Let's see if this solution has any insight. No, they just came up with a big pile of stuff. Oh well. How about this one? All right, well, this, let's see, minus x, this is the same thing as x squared plus y squared equals 3, right? If I move this over here, right? This is a circle of radius root 3. This is the, I could just look at it and go, there it is in polar, the circle of radius root 3, right? Let's do the math though. If we just mindlessly plugged in stuff, we would be like, okay, y squared is r squared sine squared theta, and then x squared is r squared cosine squared theta, and then if I move this over here, and then I could factor out the r squared, and then this is just 1, and I have r squared equals 3, or r equals root 3, right? You don't want to have to do all this, right? You want to look at it and use your intuition, turn it into something that's recognizable. This is going to be key when we do examples like this. Here's a polar equation. Convert it to rectangular. Well, let's see. If I just mindlessly switch them, I know that r is the square root of x squared plus y squared, right? Okay, so I could replace r there. I'll put that in. Okay, what about secant theta? Secant theta, let's see, that's 1 over cosine. Cosine x over r. So this would be r over x, right? So let me see, I have a 2 here. I need to get rid of secant theta, and I need x's and y's. Well, let's see, this says r's and x's. Well, I know that r is the square root of x squared plus y squared. Okay, so there's secant theta in terms of x and y. That's it, right? I just wrote down the definition. I was like, there's an r in it. I don't want an r in it. Well, I know this is r in terms of x and y, so here we go. That equation sucks, right? Totally sucks. Well, This thing is actually the same thing as x equals 2. Why is that? Let's look and see what we could do. If I, instead of just plugging stuff in mindlessly, let's manipulate this stuff. Secant theta is 1 over cosine, right? So I just replace secant with 1 over cosine. If I multiply both sides by cosine, I get r cosine theta equals 2, right? Well, r cosine theta is x, right? So just like when you see x and y, you want to replace them with r cosine theta and r sine theta, right? When you get stuff like that, what you want to do is turn it into r cosine thetas and r sine thetas so that you can swap them out with x, right? You want to go the other way as well. Because if you took this, if you squared both sides of this thing, you get this. This would be a 4, right? If you squared both sides, then you could divide both sides by that. And this would just be 1. And then multiply both sides by x squared, and then square root both sides. So yeah, this is just x equals 2. Okay. But if you just replace this stuff mindlessly, you end up with a big pile of stuff. And it's like, that sucks. We don't like square roots of x squared plus y squared, right? We like x squared plus y squared. We don't like square roots. Square roots suck, right? So when we're dealing with spherical coordinates, we end up with these square roots all over the place, right? So what you want to do is rearrange these things, try to get r cosine thetas and r sine thetas set up first, and then do your switcheroo, okay? And like the tangent theta equals y over x, right? Try to get your tangent thetas in there. You want to get r cosine thetas, r sine thetas, or tangent thetas, then switch to your x's and y's, okay? So yeah, here's a graph, x equals 2. Right? Vertical line, x equals 2. You'd never think that r equals 2 secant theta would just be a vertical line, right? The more we play with this, the more we're going to develop intuition, which will help. Just before we move on, any questions? Because y'all have your exam today. Any questions about anything? I'm not going to have office hours today because it's Halloween. I have to get my daughter ready for a little. I caught her the other day hiding in the bathroom in front of the mirror practicing her different cries. Terrible twos hit like the day they turned 2, I swear. So no office hours today. So if you have any questions, ask them now. Otherwise, we're going to get out of here. All right, let's go.